right, let's get started. Hello, everyone. My name is Ujjwal. I'm the founder of Spatial Thoughts. Spatial Thoughts is a learning platform. We create and publish lots of open training materials on QGIS, Python, GDAL, and of course, Earth Engine. We also host online live classes, which are globally accessible, and people come and learn in an instructor-led environment. I want to welcome you to this session on time series processing using Google Earth Engine. The session is going to be a lecture mode, but I encourage you to get the slides. The link is given here, the bit.ly link, and it'll allow you to access the code and the notes, etc. I also want to welcome a lot of people who are watching the live stream. Welcome. We have Santosh in the chat, and we have Justin here monitoring the live stream questions. So if you have questions, go ahead and put those here. We're going to get to that during the session. And again, I'm going to keep it quite informal. So if you have questions during the session, please raise your hands or just shout it out. We have mics here. You can come in and ask. But we're going to do a formal Q&A halfway through the session and through that. So with that, we'll get started. We're going to talk about different types of time series processing, smoothing, filtering, gap filling, interpolation, etc. These are the kind of pre-processing steps that you have to do when you work with remote sensing data. And in Earth Engine, you do this using joins. So I'm going to spend a bit of time teaching you about joins. This is a concept that is a bit hard for beginners to get their head around, and they're useful in many, many contexts. So if you don't take away anything else from the session, you'll learn about how joins are useful, and it'll help you kind of apply those in different settings. Also note that we are going to use Sentinel-2 NDVI time series, but all the techniques I show can be applied on any data set. Landsat, MODIS, even non-Earth observation data, climate data. I have an example of interpolating population time series, etc. So you can apply it on any data. The idea is to first learn the techniques, and then you can apply it on any. So why do we do this? Because anybody who has ever worked with Earth observation data, you know it's noisy. In an ideal world, if a same satellite image the same object on 2 different days, you'll have the same values, same reflectances. But that's not true. We have atmosphere between the ground and the satellite, and that introduces noise because we have clouds, aerosols, etc. We also have gaps in our time series. We have cloud. We don't know what's going on underneath. So we need to do something with this gap. And because of this noise, you have a very signal that is not the true value of the signal that you're trying to get. And you want to clean it up, remove the noise, and get to the true signal. So this techniques allow you to get to that. So let's get a time series. We'll start with Sentinel-2 collection, and we'll select a point. This is coordinates of a point in northern India. They have dual cropping cycles. They have 2 crops, so you can see this nice NDVI changed during the year. We'll take 2 years worth of data, so 2019 to 2021. And we'll apply some filters. We'll remove very cloudy scenes. So we'll take any scenes which have more than 30% cloud. We'll just remove them from our time series. We'll add some masking. So we'll apply a masking function and mask clouds which are known. Cloud masking is not perfect. So whatever information we have in our images, we'll say we want to remove the known clouds and mask them. And finally, we'll map a function to add NDVI band to each of those images. And you end up with something like this. At this point, we have 97 images over the 2-year span. And each image has 13 bands, 12 bands for the Sentinel-2 data, and we added the NDVI band. You have all these images, and we can now look at it, and maybe at that point, we'll construct a time series chart. And this is what we get. This is our time series. On one hand, you can see the cropping pattern. You can see this cycles of crop growth and harvest. But you also see it's very noisy. You see in the middle, there's a sharp drop. And that's not physically possible. NDVI doesn't go down that much in 5 days and come back up, right? That's because maybe there was a cloud there, which we couldn't mask. And the clouds will reduce the NDVI. So you have that drop. You also see that over a shorter period, there are this noisy pattern where it goes up and down, the slight variations. And again, that is due to the noise in our data. We also have gaps. If you look towards the end, the 2020 09, you'll see that there's a gap in the observation. That is because we masked out a cloud at that point. So we don't have an observation there. So we'll learn techniques of how to kind of improve this time series, improve and get to the true signal on this data. And we'll start with a simple approach, and we'll add more complexities and more advanced techniques that you can apply one after the other. We know our time series is not one-dimensional. Earth observation time series are images. So if you look at this time series as an image, you'll see this is what our time series looks like. And you can see that there are missing images, there are holes, there are aberrations where you can see suddenly stuff jumping in and out. So this is what a time series looks like. And when we are working with Earth observation time series, we have to work with all the pixels. And one of the great things about Earth Engine is you have a time series at every pixel, and you can apply functions to create and process those at every pixel. And you can improve your data. Right, so let's take this and see what we can do. So the first technique I'm going to show is the moving window smoothing. It's a simple technique where you take a time window and compute the average within the time window and replace the value with that value. So this allows you to remove this fine-grained variations at each step, where you select the time window, maybe say, in this case, we'll take all observations within a 15-day period, and for that particular observation, we'll replace it with the average of the 15 days before and 15 days after. And that allows us to get a smooth time series. So we have a time series. How do we do this? We need to take each image in a series, and for each image, we need to find images within a time window. So for example, if we are trying to compute the moving average at this point, we want to now find all images that are before and after that fall within this time window. And once we have found these 3 images, now we have 4 observations in the time window, including the point that we are trying to smooth. So we have these 4 observations. We want to take those and replace the value of the point with the average of those observations. Now, how do we do this? And we have to do this at every single point. We have to do this at every pixel, at every interval in time. So how do we do this? Earth Engine makes it easy to do this using joins. Okay? So I want to spend some time teaching you about joins. So joins allow you to take one collection, image collection or feature collection, and find items from another collection and join them together. This is very much like if you worked with spatial data, if you've done spatial joins, you know what that is. In Earth Engine, joins can work with image collections as well. That's why it's a little hard to wrap your head around this thing if you're coming from the GIS world. So you can join one image collection to another image collection. Why would you want to do that? Well, data fusion. If you want to, say, build a model to predict Sentinel-2 image based on Sentinel-1, because Sentinel-1 can see through clouds. And also, Sentinel-1 can predict vegetation growth. So maybe you want to fill holes in your Sentinel-2 data with Sentinel-1. So you need to find images collected by Sentinel-1 on the same day there was a Sentinel-1 image at that location. And you have to do this. You have this millions of images in one collection, millions of images in another collection. How do you find at each step the matching images? So you would do a join. So data fusion is a very common use case. You can join the same collection with itself. So for each image, you will say, I want to look at images from the same collection, which is what we're going to do. And we can find images from the same collection that match certain criteria. You can join a feature collection to an image collection. So you have a vector layer, points, polygons, and you want to join with an image collection. Why you want to do this? Well, this is great for data extraction. Say you figured out a way that you built a model to detect damage after a natural disaster. And you say, I want to test my model. So I have 1,000 locations of natural disaster over the last decade, and I want to find images right before and right after each event. Each event occurred at different times. So I need to go through each point, find the image before and the image after. And each image has this stored as the value of the date in the property. That becomes quite challenging. So you take this feature collection and you join it with an image collection and say, find images based on the property of the feature collection. And you can find those images. So great for data extraction. You can join a feature collection to feature collection. So vector data to vector data. This, all the GIS folks would know. This is what we call spatial joins, spatial queries. And if you don't know, Earth Engine is also very good at vector data processing. So if you have done like all of the GIS operations in Earth Engine, they work quite well, and you can do a lot of the spatial operations using joins. Okay? So you can do count points and polygons and stuff like that. I have examples with code in the supplement section of your slide deck of all of these examples, so you can check it out later on once you learn about joins. Okay, so how do we use joins? We need to do 3 things for using joins. First, we need to figure out what join we're going to use. There are different types of joins in Earth Engine. These are all the different types of joins that are available. The first ones are the most commonly used. And the way they work is you take items from the secondary collection that you're trying to join and save the matching images or matching features as properties on the primary collection. So if you have an image and you found 4 matching images based on your criteria from the second collection, they'll all go as properties of your first image. And you can define criteria. You can have save all. That means find all images and do this. You can say save best. You can specify criteria. Give me the best, the closest image in time. Or save first. Just give me any image that you find, right? So you can have that. And there are other joins as well. So first, you select a join. Next, you select filters. Everybody who's used Earth Engine has used filters, but these are different kind of filters. Remember when we applied the cloud filter on our time series, we said, give me all images, cloud cover percentage less than 30. So we are comparing a property of an image against a number. Here, what we want to do is we want to find all images that have the same timestamp. So we say timestamp from one image match with timestamp from another image. So these are binary filters. And they have similar sounding names, like if you have used EE filter EQ equals to this, there's a filter called dot equals, which is a binary filter, which allows to check 2 properties of 2 different collections and match them. So when you're using joins, you need to use a binary filter. And there are some filters available. We have spatial filters. You can find images have the same intersecting geometry or within certain distance. Or the most commonly used is the max difference filter, because it allows you to compare images with the timestamp. So you get a join, you select a filter, and then you apply the join. So you say join.apply, select your collections, a primary collection and a secondary collection, and the filter. Okay, so you get items from the primary collection joined with your secondary collection. Yeah, let's see this in code. It'll become much clearer. So we are doing a moving window smoothing, that we want to take each image, find other images within the span of time, and then we want to join. So first, we select our time window. Here, we're using 15 days, and we'll convert to milliseconds. Earth Engine timestamps are stored in milliseconds, so it's easier to compare if you're using milliseconds. Then we start a join. So first step, as I told you, define a join. What join we want to use? We say, I want to find all images within the time window. So we're using a save all join. If you just want to find the closest image, you'll use save first. But here, we just want to use save all. Find me all images. And once you find these images, store that in a property called images. This is what the matches key says. When you find a match, create a new property in my primary collection. For each image, store it under that. That's our matches key. Okay. Next step, we just find a filter. If you remember the filters I showed you, what filter do we want to use? We want to find all images within a time range. So we use the max difference filter. We'll say, on the primary collection, you have system:time start, which is a timestamp. Compare it against the timestamp from the secondary collection. And when you find everything that is within that difference of milliseconds, that's a match. Okay? So we have a join, we have a filter. Last step, we apply it. So we say join.apply. And here, we just want to join the collection with itself, because for every image, I want to look at images in the same collection. So the primary and secondary collections are the same, and we have the diff filter. Okay. Once you do the join, this is what happens. You get your 93 images that you had. Each image will now have a new property called images. These are the images that got matched based on a join. So you have your original images and with 14 bands, and you get another 4 images that were within this time window, each with 14 bands. You get that as a property. And this is also kind of thing that when you think about images and how we do things on desktop, you typically don't store images and data as properties, right? It's like your attribute table, you don't store stuff. But in Earth Engine, that's where things end up. So you have a property where you have actual images stored within that. So we need to get them out and do some processing. So now we have these images in a collection. We have, for each image, the 4 matching images. We just write a function saying, for each image, extract all those images and compute the mean of that. So here, the function matching images dot reduce, e-reducer mean, will just give you an average image based on the 4 images that we extracted for that image. And we want to keep the original bands. So we say, keep our original 14 bands and add the smoothed bands to it. So that way we can compare both of them. Many people like to use median here. That's also appropriate because median is less sensitive to noise outliers. So if you have cloudy pixels that got escape masking, that'll work better. So you can change this to median, and that also will work. And you apply it on your collection, and now you have a smooth collection. Okay, let's see the result. So for each image, now you started with 14 bands. You ended up with 14 more bands, which are smooth based on the images that were found within this 15-day window. And you have those as bands in the image. So this is also multi-spectral smoothing. We're not just smoothing NDVI band. If you want to see how another band was smooth, you can just pick up that and check that. So we started with this time series, a lot of noise, a lot of gaps. And this is what the time series looks now after applying the smoothing. Okay, so you can see a lot of this, the drop that you see, sharp drop, that was replaced by the average of the images around. So you have smoothed the aberrations, and we have filled the gaps with the adjacent values. And you have a much better looking time series chart. But the real magic happens when you look at it from the perspective of the images. We have images, right? We have smoothed these images. How does it look? This is what it looks like. On the left is the original collection, and on the right is the smooth collection. So you'll see on the left, you'll see a lot of this jankiness. You'll suddenly see some pixels jumping from brown to green, which is NDVI, low NDVI to high NDVI suddenly. And on the right, you'll see that it's gone. All the gaps are gone because we smoothed that out. And you can see already that the right images look much better, and they are much closer representation of how the phenology changes on the ground. Okay? It's not perfect. We're going to improve on this technique, but this gives you a preview of this technique using joints where you can apply this technique. And if you've done this before and you've said, OK, can I fit a regression model? Of course, now you have 4 images, fit a regression line, and then you save the output as an output. Or can I do a weighted interpolation? Or can I do a weighted smoothing? You can do that. So again, now you know how to get temporal neighbors for each image as properties. You can extract and do something and improve that. Okay. We'll skip this live demo. I don't have my computer, but you can try this link. Click on this link, and there's a geometry import. Delete that. Drop a point anywhere that you like in the world, and see the time series and see the smooth version of that. Right? So I'll let you play with it, but I'll pause and take questions as we are working on. So you feel free to shout it out, or you can come to the mic and ask questions. And Justin, if there are live stream questions, you can let me know. Great, I've done such a great job. Nobody has any questions. Excellent. Yeah.
What if there are no images in the time series? How do you deal with that?
Oh. So what if there are no images in the time series? So in the moving window that you chose, if there are no images, it's just going to be empty. So you're going to have a break in your smooth time series as well. And you can try this in your time series as well. Pick a very cloudy region, and you may not have any images within 15-day or 20-day window. So you have to increase the time window to find images from this thing. And even if you don't have observations, you don't. And then it becomes the challenge of, if you have a long enough time series, you can kind of fit a model to it and then fill those gaps. We'll come to gap filling as well. But yeah, you are limited by the observations that you have.
What
Yeah, the question is there a standard or preferred method for smoothing? So there are different techniques. There are research done on the effect of different smoothing methods. If you look at the first slide where I say Earth observation data is noisy, I have linked to a paper which compares different smoothing methods and the ability to extract the real value. So they compared the ground validated NDVI against different smoothing methods. And as we go, I think they found that the filtering method, the advanced filtering that we'll cover in the last section, the Savitzky-Golay filter, that actually approximated the actual signal much better than other methods. So there are methods, but again, they're more complex, so add complexity to your code, but at least you can start. So we'll kind of build our way to the more advanced technique. I've also seen people use regression model where you fit a regression line on this temporal neighbors and fit that.
Hi. If there's an instrument that I'm using that doesn't necessarily have another equivalent that can fill in, can I reference the data set itself and maybe look over a longer time window to achieve the same smoothing? Or would that be the same effect as basically just averaging over that period for that imagery?
So you don't have enough observation in the short time and you want to expand the time. Yeah, so you can, if you expand your time window, you'll get more smoothing over the time, and you can also do gap filling, which we're going to talk next. So if you don't have observations in the immediate temporal neighborhood, you can say, I want to look back 45 days and find an unmasked pixel. I don't want to replace everything. I have this pocket that is masked with cloud. I just want to fill that with the value. So you can interpolate and fill that value. So you can, typically it's done a linear interpolation, or you can, so this smoothing method doesn't account for time. Like you might find an image which is 30 days before and 5 days after, and you'll smooth everything. You'll just take an average of that. We'll learn about linear interpolation. We'll give more weightage to images that are closer, and you can do this. And you can do bilinear or cubic interpolation as well.
Great, thanks.
Yeah. Great, so let's move on. We learned the basic technique. Let's improve upon what we learned. We'll learn about this gap filling technique. Many people who are scientists say, oh, I don't want you to touch my observations. This is the satellite observation. Why are you changing those values, right? Those data I want to keep in the original form, but I just want to fill the holes because many observations will require a gap-free time series. So I have master cloud. Can you just help me replace those pixels? Don't touch anything else. And this is quite helpful. So we'll just take value from the temporal neighbors and fill those gaps with an interpolated value. And this is typically useful for cloud. We've also applied this technique on, say, population data. We have population data collected every 5 years. What if you have a model that expects a population value every year? You can interpolate and fill those gaps, right? So gaps can be artificial, like what we want to fill those gaps, or we have a cloud and we want to fill these gaps. So here, same thing, we select a time window, we find all images before and after, and then we take the after images and we create a mosaic. So we sort them, put them on stack on top of each other, and create a mosaic. The mosaic function will take the first unmasked pixel that it finds in the stack and creates an image. So that means if I have a cloudy pixel today, I go back 5 days, it's still cloudy, I go back 5 more days, and that's a cloudy pixel, I'll pick that. I go after and say, okay, I have immediately in the next neighbor, I have a cloud-free pixel, I'll pick that, right? So it's going to pick the first cloud-free pixel in your time series and use that. So now we can do this join, but we need to kind of add some extra bits to our join to get this happen. Okay. So let's go through this. So we have a time series. What we'll do is we'll apply, we have this gap here. You can see there's a gap in the observation. So how do we fill this gap? So first we define a time window and find all images that come after. So there are 3 images that are collected in the time window after the gap. And we traverse that and find the first unmasked pixel, right? So that doesn't mean that if my first image is non-cloudy, I'll just pick that. But if it was masked, I'll go back, right? So it doesn't mean if my time window is 45 days, I'm going to pick pixel from 45 days ago. That's a window to how far you want to look. And as soon as we find the first unmasked pixel, we're going to use that. So here you can see this next observation is available. You use that, do the same thing for before. find the first unmasked pixel. And then you know each pixel, you know at what time that observation was done, you know the after one, what time it was done, and you find what would be the likely value at that gap. Right? You linearly interpolate the data, and you replace it with that. Okay? So to do this, we need to know the time of each pixel. And again, this is one of these other difficult things to grasp, because we know a time of an image. That image was collected this time. What time a pixel was collected, how do we know? Well, we just create an image with the timestamp. So for this image, every pixel was collected this time. And why do we need that? Because when we create this mosaic, different pixels might be from different dates, because some pixels are masked, some pixels are not masked, and when you flatten that out, the top pixel might be coming from different time. And when you're linearly interpolating, you need to know where this pixel came from. So the first step we need to do is we want to add a band containing the timestamp, so we can identify where each pixel came from. So we use this function, image.metadata, which will extract the metadata value. So this will be our timestamp in milliseconds, and it'll create an image where each pixel's value is that metadata value. And it'll add that as a band to the image. So now all the operations we do is going to use that image, the value, and you're going to get that as a band value. So when you create a mosaic, you identify each pixel. You'll have a value of the timestamp at each pixel, which we can use to identify where this pixel came from. Right. And we start our gap filling. We select a time window. Here I'm using a longer time window, because in this particular time series, there are many places where there are no cloud-free pixels up to 45 days before, right? So just to get time series. But if you say, I don't want to interpolate with stuff that is 45 days old, you can restrict your time series. You'll still end up with gaps because there were no observations. But again, I want to emphasize that 45 days doesn't mean that every pixel will get interpolated with values from 45 days ago. It's just going to look as far and then find the first unmasked pixel. We already know the max diff filter, but if we apply this, we're going to get images both before and after, right? We have a time window, so we need to restrict to say, I just want after images and before images. So we want to add one more filter. So here is a less than equal to filter. I say, find all images from the secondary collections which are less than where the primary collection is less than that value. Right? So you compare the timestamp and find all images that are collected after. Right? So, and we combine two conditions. We say, give me all images in this time window where the timestamp is greater than the one. So my current timestamp is less than those images. And when you combine those conditions using this AND operator, you have a filter that will look for both those conditions. And now you apply this, you'll end up with a new property called after, which contains images collected after that image within a 45-day time period. Okay, so this is again our save all join that we applied. We do the same opposite. We apply it on the same collection, and then we do the opposite. We define a greater than or equal to filter, apply it, and save it as before images on the collection. And this time we apply it, the primary collection will be the result of the first operation. So we already have those after images, and we add the before images to that, and we apply those join. It's easier to see visually what happened. So this is what we end up. Once we apply these two joins, each image will now have two properties, a set of after images and a set of before images for each image that were found within those time period. Okay, so the change from the first example was, in first example, we just did join once. We found all images. We didn't care whether they were before or after. Here, we want to know what was before, what was after, because we want to interpolate. So we want to know both of those. Okay. So now we have those images. Let's do the processing. So the first step is we want to create this mosaic. So we take the before images called .mosaic, which will create this flattened image where each pixel is the first unmasked pixel on that stack. And we have before and after. And this is the temporal interpolation. We get the timestamp of the before image, we get the timestamp of the after image, and we know the timestamp of the current image. So we apply our linear interpolation formula, t minus t1 divided by t2 minus t1, and we get the time ratio. So if the current image is exactly halfway between the before and after images, then you're just going to get an average. But if it was closer to the after image, you're going to get a weighted interpolation. You can replace it with any formula. If you want to do bilinear interpolation, just replace this formula with your preferred formula. You can get a bilinear. And finally, this is the key part here. We say image.unmask interpolated. So we have each image where there's stuff that is masked. That's a gap. So we just say, don't touch anything else. Unmask it with the interpolated value. So only those pixels which are masked, replace those. We're not just saying return interpolated. If it just says return interpolated, it's going to get the entire image that was interpolated. We don't want that. We don't want to touch those pixels. We just want to fill the gaps. Right? So that's the unmask function. Unmask function will replace the mask with the items in the interpolated image. And this is what it looks. If you just look at this one-dimensional time series, not very interesting. You'll just see when I click next, this gap's getting filled with the linear interpolated. But the real magic is on the spatial domain. Now you can see, I'm going to pause, the animation will pause where there are gaps. So you can see what happened. So everything on the left and right is same, except when there are gaps. When there are gaps, it got filled, those pixels, with the before and after images. Right? Everything else remains the same. And this is what many people require, that you don't touch any of my other observations, just help me fill those gaps. And this way, you have a gap-free time series, especially if you're working with arrays. Many times you'll read, oh, just get a gap-free time series. And nobody ever tells you how to do that. So now you know how to get a gap-free time series. Okay. All right, this is our level 2. We'll go to the next level, level 3, to build on that. But I want to pause here and see if there are questions. Yeah.
Figure it's easier for other people to hear. So let's say that I wanted to do some gap filling, and I'm doing some kind of phonology analysis where seasonality is really important. And let's say that I want to try and fill some of these gaps, but I'm very concerned that if I go too far back in time, I'll be adding in NDVIs that reflect like a previous season or the next season.
Yeah.
Would there be like an easy way to say, you know, if there's a huge hole in this springtime image, look at what was going on spring 1 year ago and fill that in or something like that?
Yeah, so I've seen this happen where you apply a filter using this calendar range filter, and you say, give me images from the same time in the previous years. And then you do a mosaic on that, and then you fill those. So I've seen this typically applied in, say, when you're doing gap filling of Landsat 7. You say, I want to do spatial interpolation, but I want to also look back and say, how did this pixel look at the same time in the last few years? And I can use that. So you can always go back and fill that. So if you don't want to go back in the same year, you can say, give me a mosaic of the past few years. And that's the calendar range is your filter to be able to do that.
Great, thank you.
Welcome. Yeah.
Hi, so I was wondering if it's also common practice to use, instead of just temporal neighbors, spatial neighbors for gap filling, or if you could do both, and if that's a lot more involved, or if that's good practice.
Yeah, so if you want to fill temporal neighbors, that's a kernel operation. So there's a reduced neighborhood function in Earth Engine. You can pass a kernel and replace each pixel with the average or a function from the neighborhood. So that's also done to fill holes based on the spatial neighbors. And you can do both. So you can do this and then also pass a filter, a kernel through, and replace those in the spatial filtering as well.
Great, thanks.
Yes.
I'm going to read us one of the online questions. Hello, since Join is such an amazing and powerful tool, I wonder if there's any situation in which we probably need to avoid using Join.
That's a good question. I believe the joins are more, you can do kind of stuff that joins are doing, using just mapping a function and reducing yourself, but joins are going to be more efficient that way. I believe if the collections are very big and you are joining something on a very complex condition, it might time out or it may take time, but I would say if you're trying to join two collections, joins are custom built for that purpose, so use that whenever there is a requirement. You don't use joins when you don't need to do that. So if you just need to work with the same collection or just doing something not involving multiple collections, you don't need to use joins. But I would believe that if you have a need, joins will be more efficient and then mapping a function and doing stuff yourself.
I was curious about the max difference. If you left it out, would it just slow everything down too much? Like, are there performance, could I pick a very large time or not have it at all, or is that just going to cause things to crash?
You could avoid it, but in this case, if you avoided it, what you're going to get is going to get all images after this. So,
right, but if you're picking the first one,
yeah.
and so say, I'd love for it to be if in 45 days, but if it's not, if it's in 60 days or 80 days, that's fine with me, just give me the first one. I'm wondering if computationally, you know, it seems like, oh, now you have this huge stack of images, so it's going to be really slow, but if it's grabbing the first, you could imagine it not actually being a big performance hit. So I'm wondering, like, if that constraint's needed to have it perform well.
It will be definitely more computation, but I'm sure you can leave it out and it'll just work fine. Why we put it there is because of the seasonality, because we don't want to fill an NDVI value too far from a different time period, right? So that's why we want to constrain it, that though there might be gaps in the result, but I don't want to fill gaps with something that is completely different, right? So if you have the constraint, leave it, otherwise I think you can leave it out. And again, for performance things, when you're doing these joins, many times you'll see that you say, I've done the join, let me add to the map and see the result. And you'll say computation timed out. You say print the result, computation timed out. And what do you do when the computation timed out? Don't get frustrated, don't post in the forum saying, what do I do? Just export the result, right? So the Earth Engine will limit computation to 5 minutes. If you can't figure out the results in 5 minutes, it's going to say computation timed out. But that doesn't mean Earth Engine can't do it. It just needs longer time. So export your results. If it's an image, export the image. If you say, I've done this smooth collection, but I can't visualize it because it's timing out. So just write an export function. Either export it as video like I've done, or in your resources section, I've linked to a couple of scripts which allow you to export image collections. So you can use Python, or you can use the JavaScript version to export whole collection, the smooth collection as asset, and then you can import it and visualize it, right? So sometimes if you're doing long computations, it may time out, but you can always export it and then import the exported asset and work from there. Yes, Sharon.
Hi, thank you. So for figuring out that day's heuristic, what are some good solutions or tactics that you can use? Because in this case, you use 45, and the previous example, you use 15. And that really depends on people's data, but like, what are some ways that you can figure that out?
Yeah, it depends on where you're looking at. Like, know the region that you're working with. In this particular region, there are 2 crops. So the cropping cycle is just 3 months, right? So I don't want to look much more beyond that. But there are places, like if you're working in a region that doesn't change much, you can work with a longer time period. So just knowing the region, looking at the time series, just look at the time series, you'll see those curves, and you can figure out what makes sense as my time period.
Can you, in Google Earth Engine, can you have like specific regions? So when you're looking at gaps in like this certain part of the map, can you have a different sort of heuristic for days in that gap versus the gap on like maybe the western part of that region? Can you do that in Google Earth Engine?
That's a good question. I don't know if you can do different things. I would just, the way you would do this is build 2 collections. So you have 2 geometries and say, in this geometry, find all images, fill these gaps using this heuristics. On the right, fill this gap using this, and then join those results back.
Okay.
Merge those results back. And that's how you get stuff.
Okay, that makes sense. Thank you.
Yeah. And that also brings me to this thing where in Earth Engine, the mental model is many people say, I want this if and else condition. If the region is on the west side, do this. If it's on the east side, do this. And in Earth Engine, everybody says don't use if else condition. So what do? You do filter and join. So you filter out and say, I have 2 things, 2 conditions. I'll do something here with this one, something here with this, and then I merge that. So that's the if-else equivalent in Earth Engine. All right, moving on. Interpolation. So interpolation allows you to fill gaps in your data with the temporal neighbors. I'm going to cover how to create a regular time series. Many of the applications will require you to have observations at regular intervals. I want an observation every 7 days. I want an observation every year. right? And if you don't have an observation, your analysis won't work. Typically, arrays will require, some arrays operation will require regular time series. Some other, if you are exporting your data into some software, your software might expect regular time series. Also, if you're doing, say, regressions, and you have other variables, all your variables have to be at the same time step. So if you are interpolating, or if you're doing a regression between climate data, population data, and precipitation data, you need observations at the equal intervals, otherwise you can't match them. So we'll say how to kind of create a regular time series at regular time intervals. Same concept, little bit we'll build upon that. Here we have an unevenly timed space series because we filtered out all the very cloud images. We also masked data, so we might have an observation every 5 days, or maybe every 20 days, and it's not regular. So how can we just fill those gaps with that? So again, we select a time interval. We first generate empty images. So we say, I want an image every 5 days. So we just say from start date to end date, I'll generate empty images every 5 days. And then you know what to do. We'll just fill those with the temporal neighbors, right? So this is kind of taking the one step and say, oh, I don't have an image here, which is, it's a completely empty image. Because I created an image, I'll just fill it with the temporal neighbors. So you create the synthetic images based on the temporal neighbors. So how do we do this? Here, for example, here we're selecting one image every 5 days. So I create an empty image at every 5 days through the whole time period. And once I have those empty images, I run my gap filling, and we fill the gap, which is entire image, with the pixels from before and after, right? So one additional bit that we need to do is we create this empty image. Here we have multi-band data. So we say create an image with, if you have 13 bands in the original data, create 13 empty bands and have this image as your initial images. We select the time period. Here say I want every 5 days. You can do every 16 days, every 30 days, every 1 year, whatever. And then we create a list of days that we want to interpolate from start to end, and then just create those images. We just use the same empty image, but we just set a different property, so we know what was the timestamp of that particular image on that. So at this point, my init call is just series of empty multi-band images at every 5-day interval. And that's my collection to start, and I can just say, I have my collection, primary collection, join it with my NDVI collection and fill in those gaps. So we'll do the gap filling, and then we'll have our regular time series. Let's see how that looks. So here we have this time series. All we are doing is creating this every empty image and filling those gaps. So the shape of the time series will not change. You just get more data points. And you have this point everywhere. And this is required for many analyses, including the one that we're going to do next. So we just created this regular time series. And this is the view. You'll see more gradual changes. In the origin time series, if you compare, you'll have one image, 5 days, 5 days, 25 days jump. So suddenly you see this jump. Here you'll see very smooth, gradual changes, right? And again, you have clouds which are there. We've not done anything with those, but you can see more gradual changes over your time series. All right. So the last one is we did all this work so that we can apply array-based functions like this. So this was a very common question that I used to see. Everybody wants to do this. If you read the literature, this is Savitzky-Golay filter, which comes from signal processing, where you can use to filter out the high-frequency noise. And when you apply to like vegetation time series, it gives really good results. So everybody who wants to work with vegetation time series want to apply this filter on the data. So, but to apply this, we need a regularly spaced, interpolated, gap-free time series. And we did all of that, right? Now we have regularly spaced, gap-free, interpolated time series, and now we can apply. And what this does, it finds successive images and fits a polynomial through that. So you can choose the order of the polynomial. I want a third order, second order polynomial, and it takes those adjacent temporal observations, fits the polynomial through this, and you'll get those images through that polynomial. We're going to use this excellent library, OEEL Matthew is here. This is a great library, a lot of functionality here. We're going to use the implementation of the Savitzky-Golay filter from here. This is the default. This is how you initialize. You load the library. You select the order, second order, third order polynomial. And this is the default function for distance, just to figure out how far away images are. And we just apply this. So this is a function. So we just say, apply Savitzky-Golay filter on my regularized correction. So I have a regular time series. This is the max diff filter, the distance function, and the order. So this is what we supply the parameters, and you get your regular time series. So this is what it looks. So we have this time series. Once you fit a polynomial, we are fitting a third order polynomial through this time series. This is what it looks like. So first is the regularly spaced time series, and this is the one that's time series. I think it's, can you go to the next slide, please? Yeah. So this is what the results look like when you fit this regular polynomial. And you can see this would be the actual signal of the NDVI, and you can see the growth pattern without all the noise removed. And we did this, and let's look at the results side by side. So this is the regularly spaced time series. We've not done any processing on that, except the gap filling on the left, and on the right is the smooth version. And you can see the effect of the cloud is gone because you've kind of interpolated not only just a linear interpolation, but you just did the curve fitting, and the right one is much, much closer to what you would see on the ground. Right? And since this is image collection, you have this image collection, export this, and now you are ready to do your analysis. Right now you say, I want to find the harmonic parameters. I want to find the trend analysis. All of that you can do on top of this. You'll get much better results because you've removed all the noise from your data. Right. So we come to the end. We did this 4 things. We started with a moving window smoothing. We learned about joins. We then said, I want before and after images to do gap filling. Then we created a regular time series. And then lastly, we used that to do an array-based operation by doing some filtering. And since we have time, I want to show you some extra cool stuff, like what you can do joins for. And then we'll open up for questions. So this is for a project I did on predicting urban growth using machine learning. So we want to use a machine learning model to predict urban growth. And for that, you need population as one of the parameters for the regression model. And population data comes every 15 years. We have this data. But my model required me to use this every year. So we just interpolated this and created this collection of rasters using this technique I showed. And then you have those stack of images. You have a yearly urban classification, and you have other parameters, and then you can run your regression model on per pixel, and you can predict urban growth. Right, so this technique is not only limited to NDVI or observation. Whenever you need this interpolated values at each pixel, imagine this is not just interpolating a time series in one dimension. This is at every pixel. And you can do this in other software, but again, Earth Engine can do this much, much faster, and it's just much easier to work with that, so you can do this. This is the data fusion example, joining Sentinel-2, finding the Sentinel-2 and Sentinel-1 images collected on the same day or the same time period. So you select a point, and you find a Sentinel-2 image, and you'll go through the Sentinel-1 connection, find the image collected on the same day, or with a max diff filter. So you say, I want to find images collected closely, and then you get those Sentinel-2 bands, Sentinel-1 bands, and you fuse them together. Right? So this is the script that's available. This is a spatial join. So I have the census blocks here, a layer of highways. I want to find all the blocks within 1 kilometer of a highway. So I take my highway collection, join it with the census blocks collection, use a within distance filter, and you suddenly find those items which are within distance of that geometry. So that's your spatial query, so to say, in GIS software. This one is the earthquake example. I have earthquake points, and I want to find, for each earthquake, there's a different date. I want to find image that was collected right before earthquake and right after earthquake, so I can do the change detection. But it's not the same date. I can find different images on different dates. And I want to leave you with this resources. Follow up to this, Nick did an excellent tutorial a few years back where he says, now you want to fit a model to this time series. What do you do? So this is your pre-processed time series. Now the analysis, time series analysis is a great video on the developer guide. You can check it out. There is a exporting image collection resources, and also link to my talk I gave a few years back on vector data analysis and visualization. So if you are like to do GIS stuff, which I come from like doing GIS stuff, and when I discovered Earth Engine, I was like, let's do all the GIS stuff that I'm used to, and it works quite well. And so you can use this. Sometimes I use QGIS primarily, but sometimes when I have really large data, I upload to Earth Engine, do my analysis, and export it out. That works quite well as well. So that's it. Thank you. I'm open for questions.
I have actually a question. So when you have to create the regularized observations, like on the regularized time interval, I noticed that sometimes clouds are stationary. They kind of fade in and out because you're averaging across those days. But then the Savitzky-Golay algorithm, that filter somehow also gets rid of the clouds. Could you explain a little bit about how that actually happens?
Yeah, because in normal gap filling, we're just doing a linear interpolation. So if there was a cloud before, and you had some bit of cloud after, you can't just get removed because you are kind of averaging. But when you're fitting a curve, you can say now there's 5 observations before which didn't have cloud. There's one cloudy observation, and you can just fit a curve through that. So the curve fitting is more a higher order interpolation, and that can help you get rid of those kind of noise much better. So that's why many people want to do this, because a first order fitting will still not get rid of all the noise. It's still kind of doing a linear interpolation. So, yeah, but yeah, it's amazing to see when you see these curves, say, yeah, this looks great, but when you see those images, then you say, yeah, that got rid of all the noise that you had in your data. So, and again, but you need to be careful about where you're applying it, but many applications would require you to kind of have those regularly spaced data, and in that case, you can have those curve-fitted data.
If there are collections of data in the individual images have categorical data rather than continuous, like a land cover class or something, are there any variations of this technique that you could talk about for that type of interpolation?
Yeah, that's an interesting question. So you are interpolating data which are not continuous variables, so you can interpolate. But what if it was a class? What if it was a forest class being urban class? And what happened in intermediate years? Can you interpolate that? So these techniques are not directly applicable, at least not as far as I know. The way you would do this is, what I've applied this kind of time series technique is to do what we call forward and backward corrections. So for example, you are doing a time series classification. So you have, I want to generate a classification for each year, 2000, 2001, 2002. And when you do this independently, you'll end up with a lot of noise. So you have some region which was classified as forest. Next year, it was cropland. Next year, it was forest. Right? And in this case, it may have happened that in a year it turned into cropland and forest, but most likely not. So in this case, you can have some rules in your classification time series. So for example, you can have a rule that if a pixel turns urban, it was not going back to forest. That's a rule. You can make an assumption of the region that you're classifying, that if a pixel turned urban, it's not going back to forest. And then you say, for each time series, you say, what was the before pixel? Use joins to find what was the before pixel, and what's the current pixel. And if that doesn't match the rule, you replace it with the previous pixel. So if say this pixel was forest, it is now classified as urban, not likely, so you do the correction. So this is known as a forward correction, and you do backward correction, that if a pixel is forest, it couldn't have been urban in the past. Right? So you go back and say this pixel is still forest. If it was classified as urban anytime in the past, go and replace those pixels. And that correction will end up with a very smoother classification time series. And this is something I have that implementation in Earth Engine. I will add that link in the resource because when I worked on this urban classification, if you just do your classification, it's all very noisy. So once you do these corrections, you'll end up with an urban growth model where it's like, cities is growing, and it's much more suitable for modeling. So look for an extra link in these resources. I'm going to add that script here.
Thanks, that was really helpful stuff. Just wondering with the Savitzky-Golay, I'm used to implementations where you specify the window and the order. Can you go through the arguments of the OEL function a little bit?
Yeah, so you can look at the implementation. It's open source. You can look in the code. They use 5 as the window. I think that's a static value that is implemented. So there's no parameter that you can set. If you wish to do it, take that function, copy, paste it, change that, and you'll be able to do that. And Matthew is here, so talk to him about adding that as a parameter. All right, done. Thank you, everybody. Thanks for coming, and I hope to see you in person during the rest of the summit. Thank you.